In this video, we're going to start to think about how much does an individual atom weigh and how much does a group of atoms weigh, both by element and in terms of isotopes. So atomic mass. Atomic mass is the weighted average of all isotopes. So all of the different isotopes for any given element add up to 100%. And so we can use a weighted average. A weighted average is the ability to think about how much of any given part you have. So typically, a mathematical average is just add up all the numbers, divide by how many numbers you have. A weighted average is going to be the sum of the fraction of the isotope. So this is the fractional percent. And then the isotope mass. So it's important to know that they all add up to 100, and so the mass of the isotope is usually provided. For most isotopes, you would be given some part of this. So the atomic mass is and this symbol means the sum of the fraction of isotope N multiplied by the mass of isotope N for all isotopes. So if you have 3 isotopes, you would add together isotope 1 plus isotope 2 plus isotope 3. The sum of all of these isotopes would give you the atomic mass. So basically, we want to figure out what percent of the mass comes from any given isotope. So let's look at an example. So down here in our example, we're looking for what is the average atomic mass for chlorine. So in this problem, chlorine has 2 isotopes, chlorine 35, which is 75.78% abundant and has a mass of 34.969 atomic mass units, and chlorine 37, which is 24.22% abundant and has an atomic mass of 36.966. For the most part, these numbers would be provided, or you would have enough data in order to solve for one of them, like we'll see in our next example. So if we use the equation that you can see up here highlighting in blue, we're going to essentially write this out. So we're going to take the fraction multiplied by the mass, and this is for chlorine 35, and then we're going to add together to chlorine 37 the fraction plus mass. So in this case, we're going to get these numbers directly from the problem. The abundance is provided as a percent, so you can just divide that by 100. So for chlorine 35, we will have 0.7578 multiplied by 34.969. We're going to add that to the fractional abundance of 0.2422 multiplied by the mass of 36.966. So when we do this, we want to make sure that we're keeping track of our sig figs. So we're going to multiply these together, and that gives you 26.50 because the abundance controls the number of sig figs, plus 8.953 for the second number, and together that's going to give you 35.45 AMU. And so it's important to track your significant figures through this calculation, making sure to look first at the multiplication and then at the addition. So in addition, it is controlled by the value with the fewest number after the decimal point. So let's look at another different example. So in this case, we have the atomic weight. If the atomic weight of copper is 63.546 atomic mass units, and the dominant species is copper 63, which is 69.15% abundant with a mass of 62.9296 atomic mass units, what is the abundant and weight of the non-dominant species? So the abundance is 100% minus 69.15%, and that gives you 30.85%. And we were able to determine that because all of the isotopes add up to 100%. So now we can set up our calculation where the atomic mass is equal to the copper 63 plus 65 copper. And so for both of these, it would be the fraction multiplied by the mass. And so this one is a little different. We have the atomic mass, and that is 63.546 atomic mass units. And that's going to be equal to the fractional abundance of 0.6915 multiplied by the mass of 62.9296. And that's going to be added together with the fractional abundance of 0.3085 multiplied by x, which is the weight or the mass of the non-dominant species. So we're again going to set up our calculation. And so what we'll see is these two values multiplied together gives you 43.52. So 63.546 subtracted or minus 43.52 is going to give us 20.03, and that equals 0.3085 times x. And we're solving for x. Whoops. So x in this case is equal to 64.91 AMU. So the final answer includes this value and this value for the atomic weight of copper. So for any of these, what we want to think about is what is the equation and making sure that we account for the fractional abundance for each isotope. So now that we can calculate the atomic mass, we want to think about what is the mass of any given group of elements. So we know that copper had an atomic weight of 63.546 atomic mass units. So we would like to be able to use these masses within the research lab or a teaching lab. And so the reality is there are no scales that have atomic mass units as the units. They often have grams or ounces or something else. So we want to weigh our samples using the SI unit of grams. So one of the things that they decided to do, scientists, is we want to use the unit a mole. And so in this case, it's spelled MOLE, and this was developed by Avogadro. So 1 mole is equal to 6.022 times 10 to the 23rd particles. And Na is often used in annotations, and this means Avogadro's number. So in this case, you could have a mole of any given item. So you have a mole of oxygen atoms, that is 6.022 times 10 to the 23rd oxygen atoms. And so this is the unit that we're going to use. And so we are going to think a lot about moles throughout this semester or these videos. So Amedeo Avogadro developed this number. And so his number is 6.022 times 10 to the 23rd particles, or items, or molecules, or in this case, elephants, or anything else per mole. And so this is going to allow us to convert between moles and atoms. So we want the ability to say, hey, if we have half a mole of sodium, we can now convert into atoms. So for example, how many cobalt atoms are found in 3.14 moles of cobalt? So we're going to set up a dimensional analysis problem of 3.14 moles of cobalt. And every mole has 6.022 times 10 to the 23rd atoms, or molecules, or elephants, in 1 mole. And so when we plug this into our calculator, you would get 1.89 times 10 to the 23rd cobalt atoms. And that includes the significant figures. So let's think about a slightly different example. If we have a school of sardines, which are tiny fish, and it contains 1.1 times 10 to the 7th fish, how many moles of fish are in the school? A mole can be of any given component. And so in this case, we're going to set it up quite similarly, except we're going to take our 1.1 times 10 to the 7th fish, and we're going to create a mole which has 6.022 times 10 to the 23rd fish. So when we plug this into our calculator, we would get that there are 1.8 times 10 to the negative 17th mole of fish. Avogadro's number allows you to calculate between any given component as long as you use Avogadro's number. Cobalt. So I told you that there are no scales that measure in atomic mass units. There are also no scales that measure in mole. So we would like the ability to calculate how many grams something is. So in Amedeo Avogadro's calculation, he determined that 1 mole of carbon-12 atoms contains 6.022 times 10 to the 23rd atoms. It also weighs 12 grams. So what he then did was he was able to calculate the relative molar mass for any element on the periodic table. So the molar mass in grams per mole is equal to the atomic mass. So on the periodic table, we can see the atomic mass for any given element. It's going to be at the bottom. So if you look at the periodic table, and so for helium, it would say 2 He, helium, and 4.003. This number right down here is the atomic mass for any element. So using the masses found on the periodic table, we can now convert from moles of 10 into grams, for moles into grams, or grams into moles. So how many moles of 10 are found in 35.8 in a 35.8 gram sheet of 10? So 10 is a metal. How much do we have? So we're going to take our 35.8 grams of 10, which is SN, and divide that by the grams found in 1 mole. So we can find 10 on the periodic table. It's element 50. And so in this class for masses from periodic table, we're going to use 2 decimal places. For helium, that would give you 4.00. For 10, it would give you 118.71 grams in 1 mole. When you plug this into your calculator, you should get 0.302 moles. So let's look at a couple of different examples. So in this case, we are mining for gold, and you found a 1.34 gram nugget of pure gold in this case. How many moles of gold atoms are in the nugget? So in this case, we are going to calculate 1.4 grams of gold, which is AU. Then we're going to use the molar mass of 196.97 grams and 1 mole of gold. And that's going to give you 0.00680 moles of gold. So in addition to the moles, we also want to know how many atoms. Because we know that 1 mole contains 6.022 times 10 to the 23rd, we can take this moles of gold and convert that into atoms. So we're going to take our 0.00680 moles of gold, and 1 mole is equal to 6.022 times 10 to the 23rd atoms. And so there are 4.10 times 10 to the 21 atoms of gold in the 1.34 gram nugget. So we should be able to convert from grams to moles and moles to atoms. We can also convert from atoms back to grams. So in this next example, a reaction utilizes 3.79 times 10 to the 45th calcium atoms. How many grams of calcium are in the reaction? So we know that 3.79 times 10 to the 45th atoms are in this reaction. And we know 6.022 times 10 to the 23rd atoms in 1 mole of calcium. And based on the periodic table, we know that 1 mole of calcium is 40.08 grams of calcium. And so we don't have to go through each of these steps individually. You can set them all up. I would recommend that you show all of your units, but when we plug this into our calculator, you would get 2.52 times 10 to the 23rd grams of calcium. So at this point, we should be able to convert from grams to atoms or atoms to grams, and we're able to calculate the atomic mass of any given element.